Good morning, students. I welcome you all again for this session. So today we're going to solve one problem of this second type, and in the next class we're going to start with the next chapter. Okay, so the problem is like this: a singly reinforced rectangular beam is subjected to bending moment of 75 kilonewton meter at working loads. Design the beam for Flexure. Okay. The materials used are M20 grade concrete and Fe415 steel. Provide effective depth 1.5 times the breadth. Okay. So try to understand what is the difference between this problem and the previous problem what we have solved. Okay, it is a singly reinforced beam which is subjected to bending moment of 75 kilonewton meter at working loads. Means at working loads the moment will be 75 kilonewton meter. Means it is not a factored moment, it is working moment. It is M, not Mu. So M factored moment is Mu, but here it is M is given. So working moment M is equal to 75 kilonewton meter at working loads. So now we're going to design the beam for flexure. Flexure means bending. So when the load comes, the beam will going to bend. So that is called as flexure. So here they have mentioned design the beam. Okay, try to understand this term design. Here B is not given, width of beam is not given, effective depth is also not given, and area of steel is also not given. Okay, so it is somewhat the design you will going to make. Okay, so but condition given is what? Provide effective depth, that is small d, is equal to 1.5 times the breadth. Okay, small d is here, width of beam b is equal to, write down as it is, we have to calculate. Then effective depth small d is equal to 1.5 times of this b, 1.5 times of width of beam. Then working moment, this is working moment, 75 kilonewton meter. Okay, so therefore multiply 1.5, will get factored moment. So factored moment is equal, mu is equal to 1.5 times this 75. Okay, so that is equal to 112.5 kilonewton meter. Okay, so moment, working moment multiply by the factor of safety, that is 1.5, will get mu. Okay, so mu is equal to 112.5 kilonewton meter. Effective depth d is equal to 1.5 times of breadth, and b is equal to as it is. Now first we'll find out the dimension b and d, then we're going to find out the area of steel. So if you want to find out the dimension, okay, what we're going to do? Equate, okay, whatever the given bending moment is there, mu, equated to mu limit. Okay, so this mu given moment of resistance is equated to mu limit. So mu is equal to mu limit. So mu is 112.5. It is kilonewton meter. Okay, so this whole divided by 10 to the power of multiply this with 10 to the power of 6. Means if you multiply 10 to the power of 3, kilonewton will become newton. Again if you multiply 1000, meter will becomes millimeter. Okay, so this 112.5 into 10 to the power of 6, now it becomes what? Newton millimeter. So 112.5 into 10 to the power of 6 Newton millimeter, that is equal to, what is mu limit? Now see, for grade is Fe415 steel. So for this grade of steel, what is mu limit? Mu limit is equal to 0.138 FCK BD square. Okay, so substitute the values, 112.5 into 10 to the power of 6, that is equal to 0.138 into FCK is 20, okay, into B, keep B as it is, B, and D, effective depth is equal to 1.5 times of B, 1.5 B D square. Okay, so 112.5 into 10 to the power of 6, so this becomes 6.21 B cube. Now see, So what we're going to do, 1.5 square, 1.5 square into 20 into 0.138, so that will becomes 6.21. Then this b and then b square, so it is b cube. Now it is a cube. So b cube is equal to 112.5 into 10 to the power of 6 divided by 6.21. So b cube will be 18.11 into 10 to the power of 6. Now b is equal to cube root of, no, b is equal to cube root of 18.11 into 10 to the power of 6. So we're going to get 262.6 mm. Okay, it is in the fraction. Okay, so rounded off to next higher value. So we can write it as, so width of beam b is equal to 270 mm. B is equal to 270 mm. Now this is B, and what is the condition given? Effective depth D is equal to what? 1.5 times of B. So effective depth B is equal to, okay, 1.5 times of this B. So that comes around 405 mm. So in the first step we have found out the dimension, that is width of beam and effective depth of the beam. Okay, next we are going to find out the area of steel. Okay, so area of tension reinforcement, that is AST. So we know that we're going to use this formula. Mu is equal to, okay, moment of, that is ultimate moment of resistance. Mu is equal to 0.87 Fy AST into D into bracket 1 minus Fy upon Fck into AST upon BD. Okay, so again substitute all the values. So mu is 112.5 into 10 to the power of 6, 0.87, Fy is 415, AST, then effective depth 405, 1 minus 415 divided by 20 into AST, keep as it is, divided by 270 into 405. So 112.5 into 10 to the power of 6 is equal to, okay, so now multiply this term first, multiply this into 1, okay, this term, that is 0.87 into 415 into 405 into 1 AST, okay, again multiply this term with this term, we are going to get this 27.74 into AST square. Now rearrange the terms. I'll take this term this side, so this becomes plus now. So 27.74 AST square, then again this minus, this term comes here, minus 146.22 into 10 to the power of 3 AST, and this is as it is, plus 112.5 into 10 to the power of 6, here it is be 0. Now see, again it is in the form of ax square bx plus c is equal to 0. This is a quadratic equation in terms of AST. So what is the solution? Minus b plus or minus square root of b square minus 4ac divided by 2a. Now write down the terms. A, this is a, with sign you have to write. A is equal to 27.74. B, this is b is equal to minus 146.22 into 10 to the power of 3, and c is equal to plus 112.5 into 10 to the power of 6. So substitute these values here. Okay, we are going to get the area of steel. AST is equal to 935.37 mm square. Okay, area of steel is equal to 935.37 mm square. This is the quantity of steel required for this beam. So in this problem, first we have found out B and D not given. Okay, so equating this total mu to the mu limit, we are going to get the B, and condition D is equal to 1.5B, we have got D. Then using this formula, okay, we have found out the area of steel. So whatever the problems, these three problems we have solved, okay, are second type of problems. Okay, so now try to understand what are the first type problems and what are the second type problems. So in first type problems you have solved the important problems, that is finding out the ultimate moment of resistance. Okay, ultimate moment of resistance, mu. Okay, so first that we have to identify whether it is a balance section, under reinforced section, or over reinforced section. So depending upon that, we have found out the ultimate moment of resistance. Or sometimes we will go to calculate the load UDL, which can be on the beam section. That are first type problems. And in second type problems, moment will be given. Okay, moment will be given, and we need to calculate the area of steel. Okay, so this completes the first chapter. Okay, it is not first module. Okay, in first module, first chapter is completed. Okay, so one chapter is completed, and in the next class we'll take up the second chapter of the same module, module 1 only, but second chapter. In that we'll going to calculate deflection. Okay, when the load comes on the beam, what will be the deflection of the beam, that we're going to calculate deflection of the beam, and crack width of the beam. When there is a cracks in the beam, so what will be the width of crack, that we're going to find out in the second chapter. Okay, so in the second chapter we'll find out deflection and crack width. Okay, again now we're going to solve the problems, but till now in the first chapter, in the beginning we have seen that the different methods: working stress method, okay, ultimate load method, and limit state method. Then we have seen difference between working stress method and limit state method. Okay, then we have considered balance section, under reinforced section, and over reinforced section. According to that, we have written the equations. Then we have seen stress block parameters. Okay, so one important derivation we have done in the stress block parameters. Okay, that is you have to show that x bar is equal to 0.4 to xu. That derivation is important. Then we have started the problems. Okay, I think 5 or 6 problems we have solved on type 1 problems, and 3 problems we have solved on type 2 problems. So till now, whatever the problems we have solved and the theory questions, all these are important. Okay, so please solve once again all the problems and all the derivations. Write down the formulas, important formulas, and see that how these formulas can be used for the solving the problems. Okay, so in the next session we'll come up with the another chapter, that is calculation of deflection and crack width. Okay, so if any doubts in this first chapter, yes, you can ask me, right? And all these notes till now, whatever we have completed, all these notes I'll going to upload in the Moodle. Okay, so please log into the Moodle, and you can get all the notes. Okay, till now whatever the completed notes, right? So you can get through the Moodle. Okay, thank you very much for attending this session. Have a nice day.